Hello guys, this is the second part of mirrors, the mirrors video. Okay, so we're gonna start with RT6. All right, so they're giving us the object. This is a concave mirror, converging mirror. Okay. All right, so now we're gonna try to find the focal point. Okay. So basically what this means is if you come parallel to the principal axis, okay, your reflection will go through the focal point and you should hit the arrowhead of this image. So if I start here, okay, and connect these 2 points here, my focal point is right there. That's all you have to do to it. Another option would be reverse the process. So go back parallel, okay, so the reflection is parallel, and go through the focal point and connect to the object, and should get us to the same place. Okay. Now let's look at RT7. Now the focal point here should be to the left of the object because the image is virtual as is on that side. So let's see how we can do this. Okay, so we go parallel, right? We'll reflect towards the focal point, but and then you line up the image, okay? Yeah, you line up the tip of the image with this dot at point of intersection of this parallel line with the mirror, and your focal point will be here. Okay, so it's kind of like this. You reflect like that, and this extension should lead you to the image. Okay, go back to the drawings and you'll see what I'm talking about. Sorry, this is a repeat of the RT7, so we're going to skip that. Okay. All right, let's look at number 29. Okay. A negative magnification for a mirror means, now negative magnification means that the image is upside down. The image is inverted, and the mirror could be either concave or convex. Well, it cannot be convex because convex only gives you an upright image, a small upright image, so that's out. The image is upright, that cannot be right because the image has to be flipped, so B and E are out. The image is inverted and the mirror is convex. Well, it cannot be convex because convex will give you an upright image, so the answer should be just D. Okay, an object is placed to the left of a spherical mirror in front of the mirror. See here, they don't tell us if it's concave or convex. If the image of the object is formed on the right side of the mirror, okay, which of the following statement must be true? So this is going to be a virtual image because for mirrors, the image is supposed to be on the same side as the object because it relies on reflections. So now, okay, so it has to be upright because it's virtual. So it's virtual, upright, and I think that's it. It's virtual and upright. And the mirror can be either concave or convex. Okay, so the image doesn't have to be convex. The image is inverted. Nope, because it's virtual. The image is upright, and the mirror must be concave. No, it could be convex and end up with an upright and virtual image. The image is upright. Nope. So the image could be either concave or convex. That's right. Number 31. Let me see. Okay. Oh yeah, I did say that the image is upright and virtual. I said that here. Yeah, it could be both. Okay. A convex mirror, I think that's what I have here. Yeah. Number 31, a convex mirror has a focal length of magnitude f. Okay, so a convex mirror will give us a virtual, upright, and smaller image. An object is placed in front of this mirror at a point 2/3 f from the face of the mirror. So the 2/3 f is a distraction. It doesn't mean anything. Because no matter where you put the object, you're always going to end up with virtual, upright, and small. So the image will appear behind the mirror for sure. Okay, upright and smaller, reduce. Upright and enlarge, nope. Inverted, and it's not going to be inverted because it's a virtual image. So that's it. So it should be just A and B. All right, let's look at 32. If you stand in front of a convex mirror, okay, so now you know that it's going to be virtual, upright, and smaller than the object. At same distance from it as the radius of curvature, so it doesn't matter where you stand. You won't see your image. That's not true. You will see your image and you will appear smaller than you are. I think that's the one. Yep, 32 is C. Yep. 33. Sometimes when you look into a curved mirror, you see a magnified image. Okay. Now it doesn't say what kind of mirror, it just says curved. But sometimes you see a diminished image, a little u. If you look at the bottom convex side of a shiny spoon, you will see, so immediately looking at the convex side, so you're going to see yourself upright, smaller, and virtual. So you see, so the answer is C. Yep, so 33 is C. Okay. 34. Single convex spherical mirrors produce images that are, it should be virtual, upright, and small. Okay, so it should be smaller than the object. That's not true. Are always the same size, not true. Could be larger, nope. Are sometimes real. They only produce virtual images. Okay, 35. A beam of light, let me just make sure we're still recording here. A beam of light that is parallel to the principal axis strikes a convex mirror. What happens to the reflected beam? So it looks like this. Okay, so if you have your object here, it's coming this way, it's going to reflect as if it's coming from the focal point on the other side. What happens to the reflected beam of light? It appears to be coming from the focal point on the other side of the mirror. So the answer to that is C. All right, let's look at 36. An upright object is 50 centimeters from a concave mirror of radius 60 centimeters. Okay, so basically we are between the center and the focal point. The character of the image is, so it's going to be large. If you remember the drawings, it's going to be larger than the object, and it's going to be flipped. So it's going to be flipped and flipped, which means real. So these two are out, real and inverted. So because real cannot be upright. So 36 should be B. Okay. If you place an object in front of a concave mirror, which of the following statements must be true? The image of the concave mirror, so like this. Okay, and they don't tell us where. The image of the object will always be smaller than the object, not true. Because if you put yourself between F and the mirror, you're going to see a bigger image. No matter where you place the object, a real image of the object will be found. Not true. If you put yourself between F and the mirror, you're going to get a virtual image. The image of the object will always be inverted. Not true. Because if you put yourself here again, you're going to be upright. If you put yourself between F and the mirror. If you position the object between the mirror and the focal point of the mirror, its image must be upright and virtual. That's true. Go back to the drawings. Okay, so if you put yourself here, you're going to get an image that's back here, and it's larger. Okay, so the answer to that is D. 38. Yeah, I think we're on 38. Okay. An object that is 4 centimeters tall is placed 18 centimeters in front of a concave mirror. I should not have erased that. Okay. So it's like this. And the focal distance is 20. So this is F. This is C. Okay. So the object is here. So right now we know that we're going to end up with an upright, virtual, and a larger image. Okay. Yeah. Okay. What is the location of its image in relation to the mirror? Okay. So it's definitely going to be on the other side of the mirror. So I think C and D are out. It's not going to be real. It's going to be a virtual image. It's going to be back here somewhere. Okay. So it comes down to, okay, so it comes down to this to B and E. So I think we should do some math here. Yeah, so I'm going to do 1 over 20 equals 1 over 18 plus 1 over di. That should tell me how far it's going to be on the other side. So I did the math already. So di happens to be negative 180, which actually means that it's 180 behind the mirror. So the answer should be E. Okay. We could have just done the math and figured out that it's 180. Okay. Number 39. A concave mirror has a radius of curvature of 20 centimeters. So the focal distance is positive 10. Since it's a concave mirror, it's a converging mirror, so the focal distance is positive. An object has this height, so HL is placed, so that's DO. Where is the image located? So I'm going to do 1 over F. I'm going to write that formula here. 1 over F equals 1 over DO plus 1 over DI. And magnification is HI over HO, which is negative DI over DO. Okay, so this is going to be, so I'll just do 1 over 10 equals 1 over 30 plus 1 over di. So di equals 15 centimeters. How high is the image? Well, we're going to do hi over ho equals negative di over do. So hi is going to be negative 1 centimeters. Now the negative just means that it's flipped. Okay, so the magnification is going to be hi over ho, which is negative 1 over 2. So it's negative half. Okay, is the image real or virtual? Or it's virtual? I mean, it's real because it's flipped. Okay. All right, let's look at 40. An object 2 centimeters high. Okay, so that's basically my HO is placed 5 centimeters from a concave mirror. So this is positive 10. The F is positive 10. How large is the image? Okay, so what we can do here is we can find di first. 1 over F equals 1 over do plus 1 over di. So di is equal to negative 10. And that should be expected because our object is halfway between the mirror and the focal point. Okay, so now we're going to do the magnification equation. Hi over ho equals negative di over do. So hi should be equal to positive 4 centimeters. So that's a virtual image, okay, and it's upright because the hi is positive. Number 41. Okay. A convex security mirror in a warehouse has a radius of curvature of 1 meter. So since it's convex, the focal distance is negative half the radius, negative 0.5 meters. A 2 meter forklift, okay, so that's HO, is 5 meters from the mirror. What is the size and location of the image? So let's find out what the location is. 1 over negative 0.5 equals 1 over 5 plus 1 over di. Di equals negative 0.45. So the negative means that it's behind the mirror. It's somewhere where it's not supposed to be. Okay? The reason for that is because mirrors rely on reflections to create an image. So we found the location. Let's find out what the size of it is. Hi over HO equals negative di over do. So Hi equals 0.18, positive 0.18 meters. So it's upright and it's virtual. So just be careful for anything that diverges light. The focal distance has to be negative. Okay. An object 20 centimeters in front of a mirror, convex mirror. So this is also telling us that the focal distance is negative already. But if they tell us that it's positive, we have to make it negative. Find the location of the image. So let's see what I can do here. So 1 over negative 15. This is going to be 20. So di is going to be negative 8.57 meters. And that's the negative means that it's behind the mirror, which means it's virtual. Okay, the magnification is just going to be negative di over do. And that should be equal to, I didn't do the math here. .57 divided by 20 should be about positive 0.43. No units. It's a ratio of distances. Okay, 43. A convex mirror has a focal length of negative 12. So I'm going to do, let me just scroll here. Okay. So this is DO, this is F. Okay, so we're going to just make this negative 12 and make this 60. So DI equals negative 10 centimeters. Okay, what is the magnification? Well, M equals negative DI over DO, so it's positive 1/6, which makes it a virtual and reduced image, and that's expected. Let's look at number 44. A convex mirror is needed to produce an image 3/4 the size of the object. So HI over HO is equal to positive 3/4. And the reason for that, because it's a convex mirror, so which means the image is going to be upright. Okay, so this is DI, but it's negative because it's behind the mirror. Where should the focal length be? All right, so let's see what we can do here. So we're going to do 1 over F equals 1 over DO plus 1 over DI. So 1 over F equals 1 over plus 1 over negative 24, which means minus 1 over 24. So I think this is also equal to negative DI over DO, which means that DO is equal to 4/3 or negative 4/3 di. Yep. Okay. Negative. So let's find out what this is actually. It's going to be, well, actually, hold on. Yeah, so 4 times 24. Yeah, that's positive 32. So we just plug in positive 32 here. And if we solve that, we should get the focal distance to be negative 96 centimeters. And it should be expected that it's going to be negative because it's a diverging mirror. Okay, let's look at 45. A converging mirror has a focal length of 20 centimeters. That's a positive 20. Where should an object be placed so that its virtual image will be twice as large as the object? So hi over ho equals positive 2. It's a positive 2 because it's virtual, which means it's going to be upright. And this is also equal to negative di over do. Okay, so now we're going to do 1 over f equals 1 over do plus, now if we figure out di here, it should be negative do plus 1 over negative do, 2 do. So we're just going to do this. We do a common denominator here, I guess. So it should be 1 over f equals 1 over 2 do. So do equals half of f. So it should be 10 centimeters from the mirror. Okay. All right. An object that is 2 centimeters tall, so that's your HO, is placed at the center of curvature of in front of a concave mirror. How tall is the image? Now, if you remember the drawings, you should know that the image is going to be the same size as the object. So it should be 2 centimeters high and it should be flipped. Okay. An object is placed 50 centimeters in front of a concave mirror with a focal length of 25 centimeters. Again, this object is placed at the center. What's the magnification? Now we know from the drawings that if you put an object at the center of the curvature, you're going to have the same size but flipped. Okay, so the magnification should be -1. Okay, a convex mirror with focal length of magnitude 20, so that's a -20. Okay. If an object is placed 10 centimeters in front of the mirror, on the mirror's axis, where is the image located? So let's see if we can do this. So we're going to do 1 over f, well actually I'll just write it, 1 over -20 equals, or I'll put the negative here, doesn't matter, let the calculator do the work. 1 over -20 equals 1 over 10 plus 1 over di. Now we should get a di that's negative. Okay, so anything that says in front of the mirrors is no good. These two are out. Okay, so now if we do the math over there, we should get 48 -6.67 centimeters. So it should be C. Yep, that's what it is. Okay, a toy is 14 centimeters in front of a convex mirror, right? Okay, so this is DO. If the image of the toy is 5 centimeters behind, so that's negative, that's DI. What is the focal length? So it should be easy. 1 over F equals 1 over 14 plus 1 over negative 5.8. Now you can do this in the calculator. You can do 14 negative 1 plus negative 5.8 negative 1, and you can just negative 1 the whole thing later. So this should give us negative 9.90 centimeters. Number 50, a cell phone that is 8.9 centimeters tall, so this is HO, is placed in front of a convex mirror. So the focal distance is negative, and the distance, the image distance is also negative. So this should be DI is negative 7.8. And the, this is this is HI. This is negative, and that's DI. What is the mirror's focal length? So let's start it. So 1 over F equals 1 over DO, which we don't have, okay, plus 1 over DI. So now we have to go to this formula, HI over HO. So 7.8 over HO, which is 8.9. And they're both positive because it's going to be a virtual upright image, equals negative DI, which is negative 14.8 over DO. So DO here will give us 16.88 centimeters. So you just take that, plug it in here, and let the calculator do the rest of the work. So it should be, the focal distance should be negative 119.76 centimeters. So the answer to that is A, and that should do it with this video.